So now that we know the basics of limit laws, let's get into some that are going to actually make our lives a little bit easier. So using limit laws to evaluate a polynomial or a rational function. So if p of x and q of x are polynomial functions, let a be a real number, then what we can say is the limit as x approaches a of that polynomial, to find what that value is, you just substitute in that a value into your function. So in this case, we'd substitute the 2 into that polynomial. Now, if we're dealing with a rational function like we have in this example, you can do the same thing. As long as the numerator is a polynomial and the denominator is a polynomial, we can insert that a in for each. But the only time we're going to have a problem is when q of a equals 0. So we can't do this if q of a is 0. We can only do this if it is not 0. So let's look at this example. Finding the limit as x approaches 2 of the quantity 2x squared minus 3x plus 1 all over the quantity x cubed plus 4. So we can see here that we have a rational function. There's a polynomial in the numerator and a polynomial in the denominator. If you need to remind yourself of what polynomials are, please make sure you take that time to refresh your memory on that. You can go and look in college algebra for that. So now that I know this, let's first make sure, since I'm dealing with a rational function, that the denominator is not going to equal 0 when I substitute 2 in. So when I substitute 2 into the denominator, I get 2 cubed, which is 8, plus 4, which is 12. So that doesn't equal 0. So that's great, because this means to evaluate this limit, instead of having to do the limit to the numerator or denominator and then each term, all I have to do is substitute this a value, which is 2, in for x. So that gives me 2 times 2 cubed minus 3 times 2 plus 1 all over 2 cubed plus 4. So then if I simplify this, that gives me 2 times 4. I'm going to do our exponents first, follow those order of operations. All right, so that's going to give us 8 minus 6 plus 1 in the numerator over 12 in that denominator. So that we get 3 over 12, which reduces to 1/4. Okay, so now let's look at an example where I have a rational function. So you can see here we have a rational function here. We have a polynomial in the numerator and a polynomial in the denominator. But we run into an issue when I substitute 1 into the denominator. I'm going to get 0, which is undefined. So I can't use the theorem that we had on the last slide. So let's learn an additional limit theorem. If for all x that is not a, f of x equals g of x over some open interval containing a, then the limit as x approaches a of f of x equals the limit as x approaches a of g of x. You're probably wondering, what in the world is she saying here? Well, let me show you in this example, and I think it'll start to make sense. So the limit as x approaches 1 of x squared minus 1 over x minus 1. So if you think about it, and again, when we're talking about limits, we're not talking about what happens at 1. We're happening as we're approaching 1. Okay, so I want to make sure we're really getting that down. So a limit is what happens as you're approaching that value, not necessarily what's happening when the function is evaluated at that value. So what I can do is let's find an equivalent function here. So an equivalent would be, well, let's simplify this. So that's x minus 1 times x plus 1 when I factor the numerator all over x minus 1. And now what's great is that x minus 1 factor is going to cancel, and we'll be left with the limit as x approaches 1 of x plus 1. Now this is something that I can evaluate. So again, this is a polynomial function. So when I've got a polynomial function, using the theorem we learned on the last slide, all I need to do is substitute that value in for x to evaluate the limit, and I get 2.